Hello dear students, I welcome you to the 8-week online module on digital electronics and its applications organized by Department of Electronics and Telecommunication, Government Polytechnic Hingoli. So dear students, in this week we were discussing about the assembly language programming using 8086. Already we have discussed the different addressing modes and some instruction set. So up till now we have discussed the first four instruction sets, so that are up to string manipulation instruction. So today in this video we will discuss these two instruction sets, process control instruction and control transfer instruction. Along with this we are also going to discuss assembler directives. So we'll start our discussion. So next instruction set is a processor control instruction. These instructions are used to control the processor. So here we'll see these instructions one by one. So ST is used to set the bit and CL is used to clear the bit. So here we are using the bitwise operation, and this STC is used to set the carry flag to 1. CLC is used to clear the carry flag. So when we use STC, the carry flag value is set to 1, and when we use CLC, the carry flag set to value 0. Then we'll use CMC. CM is used for complement. So CMC is complementing the carry flag. So the carry flag becomes equal to complement of carry flag. Suppose carry flag is 0, then will be updated by 1, and if it is 1, then updated to 0. The next is STD, that is set direction flag, and CLD, that is clear direction flag. So we have seen the direction flag. When it is set, the SI and DI registers are incremented. When it is 0, then SI and DI registers are decremented. Then STI and CLI, these are used to set and reset the interrupt flag. So whenever we use this STI and CLI, due to this the interrupt enable flag is set, so the processor can accept the interrupts, or interrupts masking is available, and when we clear, then the processor, whenever the interrupt comes, it discard the interrupt. NOP is nothing but no operation. HLT, it is halt after interrupt is set. Okay, so the processor will halt when the interrupt is set, and it will allow the interrupt to execute its instructions. Then wait. So this wait instruction is used so when we are using a processor with coprocessor. So if there are more than one master, then wait pin is used. So wait for test pin active. So when this test pin is active, then the processor starts working. Up till this, the control, bus control or data bus control or address bus control is towards the other master. Then ESC opcode or memory. So it is used to pass the instruction to coprocessor, which shares the address and data bus with 8086. So this is also used for coprocessor. Lock. This instruction is also used to lock the bus during the next instruction. So the coprocessor cannot take the control of the address bus. Next instruction set is a control transfer instruction. Now control transfer instructions are used to transfer the control to a specific destination or target instruction. So during the execution, the next instruction address is set in the, or it is stored in the instruction pointer register. But suppose we want to transfer the control to another memory location, then these control instructions are useful. So when we execute this control transfer instructions, no effect on the flags. Now there are different control transfer instructions, unconditional transfer instruction and conditional transfer instructions. So first we'll see 8086 unconditional transfer. So there is no condition. First is call register or memory or display 816. So when we use this call register, so at a particular memory location, the instructions are stored for a particular subroutine, or it may be stored in memory, or it may be stored in a register value, or we can directly give the address of the instruction starting of the address of the this subroutine. So when we call this address, the instruction due to this instruction, the control is transferred to the given subroutine. Return, when at the end of the subroutine the return ret is used, so it will return from the subroutine to the original program. Here jmp, this is jump instruction, we can directly jump to a given memory location by using this jump. So when we call use call, it is transferred to a particular memory location. All the instructions in the subroutine are executed, but when we start when we call this jump, then the control transfer is to the particular register or memory location, and this is a unconditional jump. So here no condition is given. Then there are also some conditional branch instructions also. So there are two types of signed conditional and unsigned conditional branch instruction. So what these branch constructions do? So first this checks the flag. The flag condition is given in the instruction, so it will check the flag, and depending upon the condition of the flag, if the condition is true, then the program control is transferred to new memory location. If the condition is false, then next instruction is executed as per the given program. So it will modify the contents of instruction pointer. So here are some signed and unsigned branch instruction and conditional instruction. So this the instructions are approximately same. So here JE is nothing but jump if equal, JZ if jump if result is 0. Okay, JNE jump if not equal, which is equivalent to jump if not 0. Okay, not equal and not 0. Then jump if greater, and which is equal to jump not less or equal. Not less or equal means it is greater. So all these two instructions are equal. Here next instruction is JL jump if less than, or we can this is equivalent to jump not greater or equal. JLE, which is nothing but jump if less than or equal. JNG, that is jump if not greater. So these two instructions are equivalent, and we can use this instruction depending upon the condition in the given problem statement or program. So unconditional sign branch instruction are also same. So we can use these conditional and unconditional sign instructions to transfer the control to a particular memory location. Now, these conditional branch instructions affect the individual flags. So we can there is a flag register. So suppose we want to change the particular bit in the flag register, so we can set or reset the flag value. Similarly, we can we can check the flag value by using this control transfer instruction. So first, this is the JC, that is jump if carry flag equal to 1, and JNC is nothing but jump if carry flag is not equal to 1, that is equal to 0. JP is nothing but jump if parity flag is set or 1. JNP is jump if parity flag is not equal to 1, means it is equal to 0. JO, which is used to check if auxiliary overflow flag is 1, then it will jump to the given memory location. Jump not equal to jump if JNO is jump not overflow flag is set, that is it is equal to 0. JS, it will check the sign flag If sign flag is set, then it will jump. Otherwise, it will not jump. JNS is jump if sign flag is not equal, means it is not equal to 1, means it is equal to 0. JZ means jump if equal to 0. It will check the result, and jump not JNZ is jump not if it is result is not equal to 0, means it is equal to 1. Sorry, here we have to check. So it will be 0. Now the next, we cannot call them as instructions. These are the pseudo instructions. So assembler directives. These assembler directives are also called as a pseudo instructions. So here instructions to the assembler regarding the program being executed. So assembler directive gives directions to the assembler. Now, what is the use of this assembler directives? They are used to control the generation of machine code, and they are used to organize the program. But these machine codes are not generated for assembler directives. Therefore, this cannot be considered as an instruction, but it is directing the assembler. So these are called as a pseudo instruction. So what is the use? They are used to specify the starting or end of the program. For this we are having different assembler directives. Attach values to the variables. We can define the variable and its we can assign the value. Allocate storage location to input output data. So we can at the start of the program we can assign a particular location to store the input and to store the output. And it also define the start and end of the segment. So start and end of program we can define, and start of end and end of segment or subroutines or procedures or macros can be defined. Now we'll discuss the assembler directives one by one. DB. This DB assembler directive is used to define a byte, and it defines a byte type, that is 8-bit variable. So the given variable will have the size of 8-bit, and it reserves the specific amount of memory location to each variable. So it ranges from 00 to FF because it is a 8-bit value. For unsigned value, 00 to 7F for positive value, and 80 to FF for negative value. So we can use this for denoting a unsigned byte or positive signed byte, that is positive or negative. So how we can define this byte here? So variable name, then DB and value. So we can use like this. Here we are given example. List is a variable name, DB is a directive, and it is containing the 8-bit data, as it will store the 7F at first memory location, then 42 at second, and 35 at third. So these three consecutive memory locations are reserved for these three variables list, and each data specified in the instruction are stored as an initial value in the reserved memory location. Okay, so next is DW, which is used to define a word, means it is having 16-bit variable. It will define a word type. It will reserve two consecutive memory locations because each memory location is 8-bit. So for word we will require two memory locations. So it ranges from 000 hex to FFFF hex for unsigned value, and for signed value it is from 0000 to 7FFFF hex for positive, and for negative it is from 8000 to FFFF for negative value. Now the general form. Now it will be same as DB. So first we have to give the variable name, then the assembler directive DB, and then the value or values. We will define a variable a list. It is having word type, so we have to specify 16-bit data here, and we have assigned three values to each word. So these three variables will be stored in the 6 consecutive memory locations, which are reserved for variable this list. Okay, so because the each variable is having 8 bit size, 16 bit size, so it will require a 2 byte memory location in the memory. Next is a segment ends. So here the segment is used to indicate the beginning or start of the code or stack segment, a particular segment, and end is used to indicate end of code or data or stack segment. So here is the general form. We are going to define this segment as a segment, and when the segment ends we will use as segment ends. So inside this the instructions are or program code is written. So this segment is user defined. You can change the name here. You can change, add, subtract, anything, whatever you like to write here. So it is a user defined name. Next is a assume. So the assume is directive which is used to inform the assembler the name of program or data segment that should be used for a specific segment. So here the general form is assume segreg as segnum, segreg as segnum. So here segment register, segreg is segment register, and segnum is user defined name to the given segment register. So we will take an example here. So assume CS is nothing but code segment. Okay, so it is segment register. So CS, DS, SS and ES we can use here, and we are defining it as a code. So code segment will be assumed as this A code is assumed as a code segment, and A data is assumed as a data segment for our operations. Next. The next assembly directives are org, end, even, eqview. So org is used to assign the starting address of the program. End is used to terminate the program. So statements which are written after the end will not be executed. They will be ignored. Even means it is used to store the program data segment starting from an even address. So we have to start the location from even address. EQview, which is used to equate. Okay, so suppose we have to define some constant. So to attach a value to this variable, we will use the EQview. So we'll take an example here. So org1000h, so it informs that the program starts at memory location 100h. Then loop EQU 10feh. So loop is nothing but variable name, and it is assigned a value of 10feh. So the we can take this loop is equal to 10feh. Then next is here S data segment. So it is a data segment. So org 1200. So program starts from memory location 1200. A is byte, ADB. So A is a byte defined which is having value 4ch. So it will be this 4ch is stored in the after this 12. So it will be stored at memory location 1201. Then even means B will be B should be stored at the memory location. The A is stored at memory location 1200. Then V is word which should be stored from the even memory. So instead of starting from 1201 hex, the V is stored in 1202 and 1203. S data ends. So here this directive shows that the S data, that is this segment named as S data, ends here. Next is PROC, which is used to indicate the beginning of procedure. End P used to indicate end of procedure. FAR, so inter segment call. So suppose we are accessing the data from one segment to another segment, or the code is not stored in the particular single segment, then we will use this FAR. Near means intra-segment. So within the segment, we will call this, we will transfer the instruction pointer. The general form is like this. Procedure name, we can give the procedure name user defined as suppose addition, check, maximum number, like this. So procedure near or far, near shows we are accessing the data within the segment, and this is inter segment. Return will transfer the instruction pointer from after execution of this procedure, it will go to the main program. And here the procedure name is given, and end p means here your procedure ends. So these are some examples given for procedure. So we are writing here add 64, addition of 64 bit number, and converting from BCD to hexadecimal, like this we can write a program here, and this is a syntax. Next assembler directive is a short. So this reserves one memory location for 8-bit signed displacement in jump instruction. So whenever you use we use jump instruction, that time it will reserve a one memory location for 8-bit signed displacement. So here is an example: jump short ahead. Okay, so jump, it will jump the instruction pointer short ahead. So here the directive will reserve one byte memory location for 8-bit displacement named ahead. So this for ahead it will store a 8-bit displacement, 8-bit memory for this displacement named as a ahead. And the last assembler directive is a macro. So macro indicate starting of the macro. End m, like end p, it indicates end p indicates the end of procedure. End m indicates end of macro. General form is like this. This is user defined name, macro argument 1, argument 2. So it is same like function used in C. So we can pass the argument values here. The program statements are written in between, and after execution of this all this, the end m denotes the end of the macro. So likewise these are the different instructions or directions given to the assembler, or different instructions already we have seen which are directed for a assembler to execute a particular program. Now by using this instruction set and addressing modes, now we are going to write a assembly language program for a given problem. So in the next part we will discuss about the assembly language programming, the actual programs, how they are written, how they are executed, and what will the result, and how this result is stored in a memory location. That will be discussed in next lecture. Thank you.